By 1790, James Watt had invented a pressure gauge to measure the pressure in the cylinder of his steam engines. He also invented a way to attach a pencil to the piston so that you could create an indicator diagram. Now, you've probably seen this in your PChem class, a diagram of pressure on the y-axis and volume on the x-axis. So let's see how much work we can make a steam engine do. So now I'm going to get out my little foam core steam engine again. And I'll reset this back. And now we're going to start the steam engine. Oops. The valve fell out. Okay, now we're going to start the steam engine. We're going to open the valve, open the throttle valve, and we're going to allow the cylinder to fill with steam. So that's going to be at a certain pressure. It's going to be equal to the pressure in the boiler. Now, because the steam valve is still open, the pressure is going to stay the same. The pressure is going to be equal to that of the steam coming in from the boiler, but the volume is going to increase. So we have this situation. The pressure is constant and the volume is increasing. Now, we're going to slide the valve over. We're going to slide the valve over. We're going to slide the valve over. And the pressure here is now going to drop to that equal of the atmosphere. So we're going to see a dramatic drop in the pressure. But the volume is essentially the same because the piston hasn't moved. So the volume of the cylinder is essentially the same. Now, with the cylinder vented to the atmosphere and the steam coming in on the other side, the piston moves and the volume decreases. So again, the pressure is the same, because we've opened the valve to the atmosphere, so the pressure is equal to whatever the pressure is of the atmosphere, which is less than the pressure of the boiler, and the volume decreases. Now, we open up the steam valve. The steam is coming in from the boiler, and the pressure rises. And the pressure rises. And this indicator diagram gives us a way to measure the work of the steam engine. But it still doesn't tell us the steam engine's theoretical maximum efficiency. In other words, how much heat do we put into this thing, and how much work do we get out of it? Now, we can measure the work of a steam engine by giving it a certain amount of coal and seeing how much horsepower it produces, or we can measure the output in terms of horsepower, different pressures, operating or boiler pressures. But how can we determine how much energy we can get out of this thing as opposed to how much energy we put into this thing? And this is the challenge that the French scientists set themselves. But before we talk about that, let's think about what the scientists in the late 1700s were familiar with in terms of producing work. And what they, of course, were very familiar with, what Sadi Carnot's father was actually very familiar with, was water wheels. So in water wheels, we have a reservoir. I color this bright orange or bright red because this represents the high energy reservoir, the mill pond or the head race. This is the water high up that is going to fall to the low energy reservoir, the tail race. So the water falls from the high energy reservoir, does work, and ends up in the low energy reservoir. High energy reservoir does work, ends up in the low energy reservoir. High energy reservoir falls to the low energy reservoir, does work. High energy reservoir, low energy reservoir, falling and doing work as it falls. Falling, doing work. High energy reservoir, falling, doing work, ending up in the low energy reservoir. So this was the intellectual conception that scientists had around 1800 or so for how much work we could get from a high energy reservoir and a low energy reservoir. There's a very easy way to determine the efficiency of a water wheel or a water turbine, and that is to hook up a pump to it. So let's imagine that we have two water wheels. The energy comes from the water, comes from the high energy reservoir, falls and does work. It goes to the low energy reservoir. Now, meanwhile, the other water wheel is pumping water back from the low energy reservoir to the high energy reservoir. So while one water wheel is extracting the energy from the high energy reservoir to the low energy reservoir, the other water wheel is pumping the water back. So if 1 kilogram of water falls from the high reservoir to the low reservoir, and half a kilogram could get pumped back up, we would say the efficiency of this water wheel is 50%. If 1 liter of water fell and 1/10 of a liter was pumped back up, we would say that this water wheel was 10% efficient. If 1 kilogram of water fell down, made one water wheel turn, and the other water wheel was able to pump 1 kilogram of water back, we would say the water wheel was 100% efficient, which of course cannot be. People have been trying to build perpetual motion machines like this for centuries and failing.